Here we are. So today I will present you bandwidth efficient concurrent random communication for localization with underwater acoustic networks. It's all about underwater vehicles and localization. My name is Sliwka. I work for the Center for Maritime Research and Experimentation in Italy, and that's what I will be talking about. So, what I will be talking about is first I'll talk about our project, which is NetLBL. LBL being the long baseline. I don't know if everyone of you knows what it is. It's basically localization system using beacons. And we implement the LBL using acoustic communication and trying to do some ranging at the same time. I will be talking to you how we collect this localization data, which we'll use for localization. I will talk to you about how to encode the data so that the communication is very efficient. I'll tell you also why. And I'll show you some experimental results. And I will finally try to generalize this approach to maybe use it in other problems, etc., etc. So first, an introduction. For the introduction, I like to start with a story. So navigation is crucial in performing a mission underwater and to localize a detected object. So imagine an object of interest you want to find. Here it will be a treasure. You know, now it's the fashion with the Pirates of the Caribbean. Okay? And so we want to find this object of interest, the treasure. And so we want to send an AUV because the sea is a very dangerous place. And so we send a smart, but not so smart AUV. So an AUV which is very smart can find things and recognize it, but doesn't know how to localize it himself or itself. So it's very smart. And so we put the AUV in the water. After 25 hours, the AUV comes back. We ask the question, did you find something? Yes, I found a treasure, like 100 gold bars. And so where is it? Well, I don't know. So, well, no matter how smart it is, actually, you need to know where you are. And so there are two basic methods which are used for localization. One of them is dead reckoning, basically flying blind, where the AUV gets a GPS fix on the water and then goes down on the water and try to estimate its position starting from the first acquired position. The uncertainty grows with time, and then, well, you try to detect the object with this uncertainty. The second system is the long baseline. The classical long baseline, you deploy many nodes, buoys, underwater transponders, and the AUV is able to measure the ranges to those transponders acoustically, and then that's how you localize yourself. But well, the cost is that you need an infrastructure. The reckoning doesn't need infrastructure, the LBL needs infrastructure. So how can we do both of the things at the same time? And have the butter and eat the butter, well, still the butter. That's we're gonna use the NetLBL, and the NetLBL is in the context of having multiple nodes on the water, on the surface, ships, etc., which all have an acoustic modem and communicate with one another. And so some nodes can be on the water, some nodes can be on the surface, and provide the long baseline, the localization capability to the AUVs. Well, that's basically the story. The AUVs communicate with the surface vehicles, even between themselves. They measure the ranges, the bearings, and well, they localize themselves. Even in extreme cases, all the assets could be underwater for a while, and they could be still localizing themselves, as we've shown. I'm focusing more about acquiring ranges and using the ranges. Oh, actually, sending the information in an efficient way. That's the purpose of the tool. So these are two AUVs which are used at the center. One is with low dead reckoning capability, and this is the OAX AUV with very high dead reckoning capability. So basically, after 8 hours of the mission, it goes up, and well, we don't see the difference between the position given by the dead reckoning and the GPS. It's so good, but it costs, I think, for 1 million. Hey, So that's why it's better to pay much less and use cheap vehicles and use ranging and be able to track the solution in real time. So what do you need to localize a node I, which and the node K, node J being nodes which with known positions? You need the rank to the node J, the position of node J, you need the range and the position of the node K, and then the position of the intersection of the arcs. How do we collect data? We think of this communication. Basically, it's an exchange of messages. The node I sends a message at the measured time t1, and then the J receives a message at the time t tilde 2, and then sends back the message to the node I at the time t tilde 3, and the node I receives it at the time t tilde 4. The key is that you have a modem which is able to measure this. Not all the modems tells you when the message has been received. Not all the modems tells you when the message is being sent. So we use evologic modems, which actually do the job. Some modems, additionally, gives the angle of arrival of the acoustic wave, and those are the USBL modems, ultra short wave modems. So that's how we acquire the basic timings. Okay. Then that's how we compute the ranges. In case of synchronized clocks, which is not always the case, because we have another problem how to synchronize the motor vehicles on the water with stuff. And so synchronized clocks, in the case of the synchronized clocks case, RIG, the range between I and G, is speed of sound multiplied by T4 minus T3, the time of flight. We consider that are not synchronized, so this is not valid anymore, and so we use this formula. Delta IG is something that I knows, delta IG small delta is something that I doesn't know, that J knows, and that J has to transmit back to I using acoustic communication. So, getting a lot of notations, but J knows something. It knows the delta IG, which the node I needs for to know the range, and it knows its own position, which I doesn't know, which it has to transmit to I. So via acoustic communication in this message or in these subsequent messages. Yep. So yeah, so here we arrive to our problem, okay, which is we have the problem of localization. So we measure the range, which we derive from delta IG. We measure the bearing. Sometimes, as I told you, the angle of arrival. We need the positions of the other nodes, which we will receive or not from the other nodes, because the acoustic communication is low bandwidth, very unreliable. You lose lots of messages. And then you have the vehicle odometry. So the data recording is still on, okay? But then you correct it with the range measurements. That's the inputs. The output of the algorithm is the position of the vehicle at the time, TPT processing, which is the estimate, the uncertainty, and the validity of your solution. That's a small example. So we all know stuff. So you have an example of 4 nodes and 4 ranges to 4 nodes. One of them is an outlier. So 4 beacons, that's the object which measures the ranges, while the position is the intersection of the rings and of the boxes represent the solution. Boxes represent the solution. So now I introduced you to the problem, right? The problem of localization and how technically we try to acquire data, how it is solved. It's solved using internal methods. But then we have a slight problem with modems, and that is that so modems, especially low-cost ones, well, that's the throughput, 100 bits per second. So we used to in the air to having megabytes per second, gigabytes per second. But underwater, the speed of communication is actually very, very low, 100 bits per second. For more expensive modems, so many times more expensive, you can have for like 500 bits per second of communication, and so every bit counts. On top of that, they are what we call a medium access control, a channel control, because the channel is shared between the different vehicles, and the two vehicles cannot actually talk at the same time. So they cannot actually transmit and receive at the same time. So there is this channel sharing problem, which means one of the most famous one is the TDMA, time division multiplexing, in which one node transmits during their own time slot, and they cannot transmit here, nor here, nor here, and they have to wait for their own slot again. And so the throughput, actually, the amount of bit is actually even divided by many times. So every bit counts again. Okay. So that's the list of data to be sent by acoustic communication and the deltas, the position of the node J, the bearing to the other nodes. Note that in this network scheme, you have to send one delta per other vehicle, actually, because other vehicles are actually, well, there are other vehicles which asks you the range, right? So you have to send n-1 deltas. You have to send your own position, which is a timestamp, x and y. So if you use, an epoch timestamp, that's huge amount of bits. Deltas, we actually measure the deltas in 32 bits. So if we were to use the raw data, then we would use the 100 bits per second, just for localization data, and we have to send other things. So these are actually a simple thing. We apply a lossy and ambiguous encoding of the delta. So we use a quantization, which is a simple method of quantizing the data. So instead of having basically a continuous scale, you have quantized data. That's the first way we reduce the uncertainty, but that's not the interesting one. The interesting one is actually ambiguous encoding. Yes, which so it's an ambiguous encoding which using the modulo, and so this ambiguity appears actually when you try to decode the data. So this is the quantization error appears here. So and here appears the modulo error, the ambiguity, and P is a natural number and a known. This maybe starts to remind the thing I heard today about the quantized real strings, P, which is actually unknown to the node I. How does that affect ranging? So we have a range with no encoding in this one. And the range with encoding is actually, this is the part which is very similar, and then we have P multiplied by A being the spatial ambiguity, which I call spatial ambiguity, and epsilon being a residue due to the quantization. And that's, well, if you have a constraint, that the problem becomes this. So instead of having an intersection of two circles, two rings, you have an intersection of a bunch of rings together, but it is not a problem actually, and now I will explain you why. So how to localize the vehicle in this case? So there is the basic method is that you assume that you know your position initially. For example, when you do the GPS fix at the surface, you know more or less where you are. And so then you use that reckoning, then you get your range measurements, your uncertainty grows, and all you have to do is to make sure that the uncertainty is not bigger than your ambiguity. And after you get range measurements, then you can track the position. That's one way to solve the problem, and number two will be explained when I show you the videos. Yeah. Of the Collab MGAS 14 trial. So, it is a trial which was done in 2014. I don't remember where, but it involved a wave glider, which is a surface vehicle, two wave gliders, one gateway buoy, which is well, a buoy with a modem, two AUVs. This is Groucho, which we will be localizing, and this is Harpo. And that's the Alliance, which is the ship on which everything is stored and transferred. So you get actually, so after two measurements, you get what you saw in the figure. So many possible solutions. The square here is the ground truth. That's where actually the robot was. After many measurements, you realize that actually, so here we are not tracking actually, we're just solving the problem globally, okay? So we're trying to see all the points in all the space which actually satisfy these constraints, these constraints here. And so we find that with the specific movements of the vehicle, actually there are some solutions which become actually impossible and are eliminated from the space. So the interval methods actually decode the information and solve the problem at the same time, and reject impossible solutions, ambiguous solutions automatically. And especially if you have different measurements like bearing, which actually allow you to disambiguate the things even more. So after a few measurements, you can see that, well, for free you get the same information again. And so basically I'll show you range track off. So range track off. I'll show the video, then I'll show you the. So that's tracking in a window of 30 measurements. Okay. So that's only 30 measurements, which means that the 30 measurements we just erase the memory, so we're not tracking. So you're seeing that when you're moving in specific ways, the possible solutions they actually disappear here, and then reappear here. When you do the tracking, so when we do the tracking, what gets much better? Actually, it gets more better, which means boring. So the solutions disappear little by little, and you get the position. And after a while, things disappear, and then you can localize as if you didn't, compress the data at all, right? So it works the way it works. It gets boring because you don't see many solutions. Right? And then, when you have the bearing, I just showed. The bearing is, even more boring. Very quickly, you converge to the solution and you keep tracking the solution for the very lots of minutes and so. So to finish, we have 2 minutes. So I'll try to make a generalization. And with generalization, so that's the summary of the data which has to be sent. I talked about the deltas. The same approach can be used for positions. The same approach can be used for timestamps, the bearing measurement if the other frequency measure the bearing towards you. And that's the generalization. And so you have an encoding decoding function. I will not tell the relation between, well, they're related actually. And so so you encode the natural number value with the function. So it's the modulo function you saw before plus the quantization function you saw before with the known parameters. And when you want to decode, then you decode it with the function with the same known parameters which are shared between the nodes. And a new unknown parameter which is known to actually J, but is unknown to I. Okay. And so just, yeah. So Y, K are the measurements. So that's one thing I didn't say. So this is the dynamic equation. This one you recognize. This one is the measurement equation involving the unknown xi and the measurement ytk. So ytk is actually encoded using this generic function. In the range example, p known is the number of bits you want to encode your information on. The time resolution you want for your delta. Important note, if the nodes are time synchronized, p known can be time dependent. So the nodes share the time, and so they can make the encoding of the information much more efficient. And so basically to conclude that what we did here actually transformed the problem into a more ambiguous problem by using the encoding. Okay, but then we actually solved and decode the problem simultaneously using integral methods. And you use the problem actually to disambiguate everything, and well, that's how it looks like. So we replace the measurement by this well, thing, and this becomes well, this quantized real string. P is unknown, and P could be a vector actually of things. So I presented a case of concurrent communication and localization for the purpose of localizing the vehicle and being still able to communicate. I told that reducing bandwidth is important. I presented the formulas allowing reducing bandwidth. I presented experimental results, and well, I can say that well, it's still very early. I just got the idea, and well, there's still much room to actually investigate if it's worth something, or try to investigate different encoding schemes, because when you encode one thing, actually, that's one thing. If you encode many things, you can actually encode them in a bound way. So you can bind the position with the range and try to make even more efficient encoding by choosing the right H function, the encoding function. And well, you get something like this. It's not random. And so, well, do you have any questions?
Thank you very much.
Yeah.
On the simulation you showed, it was not on actual data, but
it was the actual data.
It was actual data.
Yes.
And,
so the actual data, except the quantization, so the ambiguity, I added myself.
Okay.
So basically, I got the range measurement because I collected them, and and I basically applied a modulo on my range to say that it is ambiguous, because well, that's to be the same thing because the information is transmitted anywhere.
And you try to compare with classical techniques such as particle filter or something like this?
Well, I would say good luck with that if you want to make these things. And I think it's something unique to integral methods to actually disambiguate. Okay, and that's why I think that this might lead to something more, because actually you actually ambiguate the problem on purpose to be able to disambiguate it later, and use the power of the integral methods to disambiguate the situation. So
you mentioned that very expensive autonomous vehicle. What principles of that is that used?
why are they expensive?
No, well, they're expensive because whoever makes them sells them for that much. But what principles do they use? How does the technique differ?
Yes, you mean that directly. So basically, there's not. Well, I would say there's not much algorithmic behind it, but they're like there's the sensor. You have this inertial navigation system, INS, which comes so out of the box. You have very precise gyroscopes, very precise accelerometers, and so you measure your acceleration, very precisely, and they're using Kalman filters most likely to actually filter things even further. Then they couple it with DVL, Doppler velocity log, which actually measures the velocity of the AUV with respect to the ground. with acoustics. So you have 4 beams going down, and then when they come back, you actually measure the Doppler shift in the acoustic wave, and this is how you actually measure your velocity. This is included into this INS, which actually fuses all this data to be able to compute a very precise position at the end. So it's very sensor-based. Yeah. And well, what the problem is when you don't have bottom lock, which means when you don't see the bottom, then the solution diverges, and that's why this becomes more important. Well, not this, but using interval methods, it becomes more important because it offers a reliable way to localize the underwater vehicle. You're not relying on a very expensive INS, so you could have more cheaper vehicles. Go very deep into, well, not very deep, but in deep water.
Some other person. Have you thought about a decentralized or distributed scheme?
So that's a vague question, actually, because that's already distributed collaborative localization. Because
the way it's set.
This is already collaborative because you send your position to the others, and then you send the delta to the others, so that the others can know the ranges, and so everybody can know the ranges with respect to everyone.
This is what I mean. Each one can know.
Yes, each one can know their position, and so each one acts symmetrically. Okay. And when you send the position, well, then actually you should, which I didn't include here, send the uncertainty of the position with that, so that even if you're underwater, if you find something you recognize underwater and you contract your position, then the others can contract their position.
Yeah, that's what I mean. It's just a problem for that kind of things.
And interval methods are good because they don't provide the problem of overconfidence. So probabilistic methods have overconfidence. Interval methods
Some additional question. Thank you very much.
You're welcome.